Good morning, good evening. Thank you for joining July Global Wheat webinar. Today we have the honor to have a genomic selection team from CIMMYT Wheat Group. So Susanne, please start introducing
implementation genomic selection in the Global Wheat Program at CIMMYT. I first want to start and let's really the team in the program. We'll have 4 presenters today, but more people that really work on the subject. Next, Umesh. So the outline of the talk today is I want to quickly introduce the CIMMYT Global Wheat Program and the deployment of the genomic-assisted breeding strategy. I will then hand over to Pancho, who will give his recent experience in genomic selection in 3 of the programs. Philomin will then take over and go into more details onto the application of genomic selection in the elite yield trials in the CIMMYT Spring-bred wheat program. And Umesh will finish off talking a little bit about the progress and challenges. Next, Umesh. So the Global Wheat Program at CIMMYT really has 5 breeding programs: Spring-bred wheat program, a winter wheat program, durum wheat, hybrid, and pre-breeding program. And we have many supporting programs. I need directly to apologize that I forgot our regional offices here. We have several regional people sitting in different countries like China, Pakistan, Afghanistan, India, that really disseminate the wheat lines that are produced by the program. We have other supporting programs like the Wheat Quality Laboratory, Pathology Program, Physiology, my own laboratory, the Wheat Molecular Breeding Laboratory, a seed health unit that makes sure that all seed arrives safe in national program, and certainly the Wheat Gene Bank. Next. So if you've seen in the previous slide, most of the breeding activities are based in Mexico. Since its foundation in 1963 by Normal Borlaug, all breeding activities are really centralized in the country. Segregating populations are put through a rigorous shuttle breeding system in different locations with different environmental stresses, and they are then tested in multi-environmental trials in the north of Mexico. So briefly, these were 2 stations, 2 locations in Mexico, in the north and south of Mexico. More recently, since the outbreak of UG99, we added a new location in Kenya, Naijoro. So all the selected advanced lines are then provided through the International Wheat Improvement Network to many national breeding programs. See that on the right on the world map. So each dot really is one national testing site, so globally. And all lines are then tested on that site. Next. So this is this graph shows the most recent analysis of annual gain for yield in the CIMMYT Spring-bred wheat program. The analysis is based on the data received for more than 180 sites globally from the last 8 years, and is targeted to the elite spring wheat yield trials, or to areas in especially developing countries that are irrigated. So the results show with a genetic gain of 0.72 in comparison to the local checks, that really the wheat program continues to deliver improved and widely adapted germplasm to its targeted environments and to developing countries. Next. So this is a different way of showing the impact of the wheat program. This is an output of an economic study that has been done 2 years ago. And the graph shows the percent of spring wheat, that spring wheat varieties or cultivars that were released in different regions in the world. And in the world, you see the last bar overall. So what you can see that the impact remains very high, so that almost 50% of the lines that are released globally are CIMMYT lines or have a CIMMYT parent, and almost 75% have any CGR or CIMMYT ancestry. And these percentages are even higher in our main target regions like South Asia or Africa. Next. So these are the priority traits. So we have really a series of core traits. So these are the must-have traits that needs to be in basically every wheat variety. So this is high and stable yield potential, durable resistance to the 3 rust diseases, water use efficiency and drought tolerance, heat tolerance, appropriate end use quality, and nutritional quality. Then we have additional key diseases of global importance that are, however, specific to certain environments, such as septoria tritici, spot blotch, etc., and root rots or wheat blast. So really the target in wheat is to package all those traits together in a single or various varieties. Next. So in terms of genomics-assisted breeding, so I think we also follow that trait-based approach. So for traits that we have really find a large effect genes, so marker-assisted backcrossing or marker-assisted selection is routine. So we analyze around 30 to 40,000 samples across the wheat program annually. However, for more complex traits, we test if our populations are amenable for genomic selection, and that is the talk today. Next. Just some quick comments on the wheat genome. So wheat is where we really struggle with the complexity. The complexity is large. So the wheat genome has about 7 GB. So it's I think one chromosome arm is of the size of the rice genome. Here it says the 3B chromosome, what is the first sequence chromosome in wheat, is larger than the rice genome already. So we have one first genome sequence of Chinese spring. And in comparison to corn, for example, it's 6 to 7 times larger than corn. Next. The second complexity is the allopolybloidy. So bread wheat is hexaploid, allohexaploid, while durum wheat is tetraploid. And both these go back to 2 or 3 lineages, the A, B, and D genome. So these are wheat wild relatives that are also intensively used in breeding. So the bread wheat genome itself has 3 homologous genome, and it's often very difficult to distinguish between these genomes with the molecular markers. Next. With this, I hand it over to Pancho. He will talk more about the experience now in genomic selection in 3 breeding programs. Thank you.
Okay, thanks. I am Jose Crossa. I work in biometric statistics unit. I'll give you a brief tour of what we have done in genomic prediction. We started all this about 10 years ago. So we have done a lot of research in developing models for prediction, basically applying to wheat and maize. I will go through some results on the bank accessions, something on the pre-breeding that we do with Siva and Matthew, go to the elite breeding program, and then do show some of the prediction in hybrid wheat of Bhoja. Next. In the gene bank accessions, you know that there is a long process between the gene bank and the breeding program. We move alleles from the gene bank to the breeding program, and that might take perhaps 10 years, I don't know. The idea is that we have been doing some work on the gene bank accessions and doing some predictions, and see the proposition at that time was it is possible to speed up the flow of genes, alleles, and haplotypes from the gene bank to the pre-breeding and then the breeding program. So for doing this, we took 8,000 wheat Mexican land races accessions and 2,000 Iranian land races. These were gene bank accessions that were phenotyped by Matthew within the Masagro project, I believe. And then they phenotyped for several traits: plant height, grain yield, 1,000 kernel weight, test weight, grain hardness, the protein, sedimentation, as well as some maturity traits. Here I'm showing only these traits. And the idea was, since the bank accessions, they form what is called core subset, where they try to put all the diversity in a core subset, in a smaller set of accessions. So we use a 10% core subset and 20% core subset for Mexican as well as Iranian land races, and see how these were predicted, the rest of the 8,000 accessions or 2,000 in the Iranian and the Mexicans. And you see there that some traits, they are very well predicted, like 1,000 kernel weights, under 10% or 20% core subset. Others, other traits like grain yield was predicted with a 0.4, 0.5 accuracy, which is a common accuracy that we get when we predict the lead lines. So these particular results, they made us to think that perhaps genomic prediction from the gene bank, to the pre-breeding is something that we can think of. Next, the other part of my presentation, I want to show some results that a work that we have done with Siva and Matthew in the physiology. And for example, these are the results from the Wami population. The Wami population is a very diverse set of wheats that we have. And they have done in physiology, they have done a lot of work on this, and they have done GWAS on the Wami population. What I'm showing here are 7 models that we use for the prediction of this Wami wheat, using the CV1 and CV2. CV1 is when we predict all the accessions in certain number of environments, and CV2 is when we predict some accessions in some environments or some entries in some environments and others in another environment. You see that in general for CV1 there is an increase in accuracy when we have a model that includes genotype by environment interaction and also pedigree by environment interaction, which is basically model 6 and 7. This is one part of the work we have done for pre-breeding. The other part, next, the other part is on the international trials that the data that we have, which is basically what they call WISIT and SATIN, which are wide international trials looking for potential conditions for grain yield, as well as stress condition, and so many traits related more to physiology. And they have a large number of environments, which is site by year combination. And we have done this prediction accuracy based not in markers, but based on pedigree, because at that time when we did this a year ago, we didn't have the marker for SATIN and WISIT. And for example, when we do this analysis, we have the prediction of each of the sites in each of the years. In the next picture, we will see, next. In here, you see that these are very busy, obviously busy slide, where we have the prediction accuracy for each of the sites. You see, we have the site and year combination at the left-hand side. We have so many sites. This is for the wheat nursery. And we have the models, and we have model 7 that includes additive by environment interaction, and 6 additive by environment interaction. And you see that each of the environment, each of the site and year combination, they have a prediction accuracy. So the breeder or the researcher or the physiology can say, maybe this particular site can be, we can predict this particular site with much more precision than others. And that was a work that we did using the WISIT and the SAT team. Now I'll show you some results on the elite breeding. Next. Every year, Ravi, Leo, Velu, Julio, Suchismitha, Philomin, Jesse, and others, they have what they call EL trials. EL trials are the first step of evaluation, that they usually had about 10,000 elite lines that are evaluated under optimal conditions. So we do this prediction using the historical data that we have 4 years back, 5 years back. And these predictions were done for cycle 17-18, where we predict 9,015 lines using cycles 13, 14, 14, 15, 15, 16, 16, 17. And you see the amount and the high dimensional of the training set, as well as the high dimension of the testing set. We used different methods and models in order to make the prediction. For this particular year, Jesse, this is within the project of USAID with Jesse. And for this particular time, Jesse used a new recalling of the markers, and we were hoping to increase the prediction as compared with previous years. In the next slide, I'll show the models that we use. We use genomic by environment interaction using markers. We use genomic by environment interaction using coefficient of parentage, which is a pedigree. And then we use both of them. And also we use a model that we have been using, which is recommender system that they use a lot in Amazon and Netflix, where we use high throughput phenotyping trait. In this particular case, we use G and DBI and RE and DBI for the 2 data sets at the end of February and beginning of March for cycles 18, 15, 16, 16, 18, and 17, 18. We wanted to predict 17, 18, but we used the high throughput phenotyping of February and March because the crop is harvested in May. So we use this in the training set. So in total, we have 4 traits in each of the cycles and the grain yield that was available for the 2 first cycles. So then we predict the missing values, the 9,000 for 17, 18, using as a training 17, 16, 16, 17. And these are the results. These are the 4 models that we use in order to make prediction of the 9,000. Next. These are the results. These are the correlations between the observed values and the predicted values. For example, when we use the genomic with G by E using the reaction norm model, which is the model that basically we use using the BGLR software, we see that using only markers, we have a prediction accuracy of 0.42. This was higher than the prediction accuracy we obtained last year and the year previous to the last one, using other type of markers. When we use the pedigree itself, we get a prediction accuracy of 0.35. When we use markers and pedigree, the prediction goes up to 0.43. Now, what happened with the IBCF system, the recommender system? The recommender system uses only phenotypic data, doesn't use any marker data, doesn't use any pedigree data. Does use only the previous phenotypic data for predicting the 9,000 individuals, the yield of the 9,000 individuals in 1718. We get, using the phenotypic data from the 2 previous years, we get the 0.37. When we get on, when we predict based in one previous year, we get 0.36. I think it is a very good prediction on the IBCF, but still using markers and pedigree got much better prediction. Next. What is this? This is a graphic that shows in the right upper corner how many of the 20% individuals observed are within the best 20% individuals that were predicted. And this is 46%, 47%, almost 50%. That means that for Ravi, if he wants to select the best individuals, the best 20% individuals, he will have 50% of them are going to be well predicted by the model. I think that these are very good results that they are using, perhaps not for selection, but rather for discarding lines. And the next one, this is related to hybrid prediction, a model that we have used and developed where we have done for Bhoja, basically for the project they have, the wheat program has with Syngenta. The standard thing is just to have the general combinability, the specific combinability of the 2 parents, and then the specific combinability of the 2 parents. What we have done here is just to add one more term, which is the interaction between the hybrid, which is represented by the specific combinability, by the environment. And we have applied this model in the wheat, hybrid wheat that Bhoja has. 3 years data. Next. And you see here the prediction accuracy for grain yield, days to heading, days to flowering, days to maturity, and plant height, 4, 5 different models. You see that the models come for the pedigree by environment, the genomic by environment, and finally the genomic by environment and the pedigree by environment. There should be the model 5 should be pedigree by environment and genomic by environment. You see that for grain yield, we have a very good prediction accuracy of 0.65. And we have also good prediction accuracy for other simpler traits, like days to heading, days to flowering, and days to maturity. So this is a work that is very promising in terms of prediction accuracy for wheat, at least for this particular date. I think that this is all I have to show. Now is Philomin.
Okay, good morning, everybody. I'm Philomin Juliana, working as a postdoc with Dr. Ravi Singh at CIMMYT, and here I'm to show some of our genomic selection results for the bred wheat breeding program and how, from an applied perspective. And this is a joint work done by a lot of people involving the breeders, statisticians, and several other pathologists and quality. And we have several donors who are involved in generating all this data, involving CIMMYT, the Gates Foundation, DFID, USAID, BGRI, and Cornell and Kansas. So moving on to the first part of my presentation. So here, let me show you an outline of what we do, how we implement genomic selection in the bred wheat breeding program. So there are 5 different stages here. So the first stage here is for identifying opportunities for implementing GS, and then evaluating predictions for different traits or populations or traits, and then evaluating the relative advantage of GS over the current strategies. So this could be either phenotypic selection or pedigree-based selections. And then implementing GS for traits where there will be a high relative gain. For example, for quality or diseases where we have seen very good success with using GS, those are the traits that we will be looking after. And then transforming challenges. There are several traits that are still challenging to predict, and we just use them for doing more research and understanding why, what could be done to improve predictions for those traits. So next slide. So first step here, identifying opportunities for implementing GS in the pre-breeding program. So the first stage is where we do the crossing. So there's this stage you can use GS for selecting the parents that can be used for crossing. And then the next stage is using GS for early generation within families selections. And this is a stage where we would expect to have, for GS to have a higher relative advantage over the other methods that we use, because you can do within family selections or select for the Mendelian sampling variation here. So, but some of the constraints that we have here are these populations are too large for genotyping. For example, as you can see here, we have about 0.4 million F1 plants, and then the F2s are about 2 million plants, and then the further generations are about 150,000 million plants, even if you come down to F6, F7 stage. So these populations are very large for genotyping. And then there's also heterozygosity in these earlier generations. And one more thing that we have to consider here is there might be a low cost benefit ratio. So considering the current cost of genotyping of $20 per sample, and the cost of line development here to advance a single plant to the F6, F7 stage is going to be about $6 because labor is cheap in Mexico and land is also cheap in Mexico. So we have to bring down this genotyping cost from $20 to, let's say, about $5 to be able to implement genomic selection in these early generations. Next slide, please. Here we have the next stage here, we have about 70,000 heteros or individual plants derived F5, F6, F7 lines, and these are grown as small plots, or they are called as species in CIMMYT. So we can do grain GS for this pre-yield testing stage, but again, 70,000 lines is still, there's a high cost of genotyping associated with this. So currently, Dr. Crossa is working on implementing pedigree and HTP-based predictions. So all these 70,000 lines will have HTP data on them, and they also have pedigree data. So he's working on combining these two to predict these lines before the yield testing stage. And the next stage we have here is for the yield trials. So every year, as Dr. Crossa mentioned, we have about greater than 9,000 lines going on to the yield trials. And here all these lines have been genotyped for the past 5 years as part of the USAID Feed the Future project. So we are testing genomic selection in this generation. Next. And then the last stage is for the elite yield trials. So this is the second year of yield trials, and about 1,000 lines going to these yield trials. And we have lots of data here on diseases, quality, and agronomic traits and grain yield. So this is a stage that I am currently actively involved in testing predictions. And I'll show you a little bit how the predictions are for this elite yield trial stages. Next slide, please. So here we have the different traits. So on the top panel, you can see the different diseases: stem rust, yellow rust, and all other fusarium, canal blunt, spot blotch, septoria, and then we have grain yield in 6 different environments that CIMMYT evaluates for: optimum irrigation, drought, severe drought, early heat, and late heat environments. And in the bottom panel, we can see the different quality-related traits: alveographs, flour protein, sedimentation, yield, low volume, and so on. And there are 4 different panels here. 4 panels each refer to a set of 1,000 lines that have been evaluated from 2013-14 to 16-17 in 4 different cycles. And as you can see here, some of the diseases are really well predicted. For example, stem rust, we have reached a prediction of 0.8 for the past season. And some diseases like fusarium are still challenging because the disease is hard to phenotype. And then we have grain yield, where the predictions are about 0.6. Now, So the highest we have attained for grain yield in the EYT nursery is about 0.6 in the different environments. And then you can see quality, some of the really good predictions across years, because these are quite highly heritable, and you have about 0.7, no matter if it's a complex trait. For example, flour yield or flour protein can be quite complex, but despite being complex, we can see the predictions are pretty good for all the quality related traits. Next slide, please. So what can be some of the challenges of predicting grain yield across different environments? So this figure shows prediction of grain yield using 5-fold cross validations, which are the green bars, and they are close to 0.6. And when you start to predict across environments, then our prediction accuracies go down, and they can be less than 0.2 every year. Next, please. So we investigated what could be the reason why our predictions across nurseries are not working well. So here is a graph which shows you, if you can see the middle part of the slide, you can see 4 different years and 1,000 lines evaluated in 2 years of yield trials. And as you can see, the correlation between the phenotypic correlations between the 2 years, it's about 0.2 or 0.3. So when we use this kind of data to train the models using a phenotype that is highly variable and unstable, then our predictions go down. And that's all low heritability is about. So if the heritability is going to be about 0.2 or 0.3, that's how much we will be able to predict using our genomic prediction models. And as you can see on the top right corner, there's a graph, and CIMMYT has large yield trials. So this is a graph showing 300 yield trials across the x-axis. And you can see the 3 colors here, the red, blue, and green, represent different sections on the field. And the top panel here is a check board log, and the bottom panel here is a check cut-through. And as you can see here, this is a variability of the checks across the 300 different trials. And you can see there's so much of field variation, spatial variation here. And we are working, Dr. Crossa is working on using some good spatial adjustments to adjust for these before making predictions. So the lesson that we learned out of here is grain yield is still complex and challenging, both for phenotypic selections as well as for GS, because you train your models using the phenotypic data. And if we have a poor correlation between the years, then that's what we should also expect when we do predictions, because predictions are again based on the phenotypic data. And for estimating these G by Y interactions or genotype by year interactions, we will need large populations that are replicated in different years. And sometimes the years are hardly replicable, because every year or bring on, the season is slightly warmer or cold, or we have different weather that changes throughout these different years. So we are working on some of those G by E models as well. And Dr. Crossa is working on that to see how we could improve the predictions for grain yield across years. Next slide, please. So we also looked at what is the relatedness across populations. Is G by E a major factor, or is the relatedness a major factor that are decreasing the prediction accuracies? And as you can see here, these are the 4 different nurseries in different colors, and we have PZ1 plotted versus PZ2. And as you can see, there's not much grouping of different nurseries across 4 different years. So this is expected in a breeding program like that of CIMMYT, where we have many common parents that are reused in the crossing blocks over several years. So this, again, gave us an indication that G by E is a bigger problem than even genetic relatedness across years. Next slide, please. So we also looked at another key factor here. Umesh, you can, oh yeah. So we have differences in phenology. So when we're looking at 10,000 different yield trial plots, there's so much of other variation that needs to be incorporated into our models. For example, phenology, you have lines that head earlier, and we have about 30 days interval of heading, and you have lodging in different lines. And as you can see in the right side panel, there are 4 different, these are the correlations of the 4 different nurseries with days to heading, maturity, height, and lodging. And as you can see, lodging has a high negative, it's a pretty moderate negative correlation with grain yield. And in some years, days to heading has a good correlation. In some years, the correlation is lost. That again depends on the weather that was prevailing in that year. In some years, the plants head early. Some years, the plants head a little late. So we have lots of other variables that have to be incorporated into the models. Next, please, Umesh. So Dr. Crossa is currently using, can you go back to the previous slide, Umesh? So we're using the IBCF approach here as well to incorporate all these multiple traits when we do predictions. so that we don't do just grain yield predictions, but incorporate all the other variables that could be potentially associated with grain yield. Next slide, please. And one of my observations was that for a highly complex trait, we have to start looking beyond prediction accuracies, because the prediction accuracy can be 0.4, but you're looking at a trait where the variation is between 6 and 8 tons per hectare. So you could get lower correlations just because a line was predicted to have a 6.8 versus it had a 6.2 actual grain yield. So we also looked at how to make effective selections from the GBVs that we have. So this graph shows 2 different years grain yield, and the correlation, the prediction accuracy was 0.37 in the first year and 0.51 in the second year. And the different colors here represent lines that were not selected by genomic selection and phenotypic selection. The green one is the lines that were selected by both these approaches. The orange one shows the lines that were selected just by phenotypic selection, and the blue one shows the lines that were just selected by genomic selection. And as you can see here, pretty much a lot of lines were discarded using both these approaches, and the green part shows a lot of lines that were selected by both these approaches. So if the selection intensity is going to be 0.5, then about 68% of the lines will be selected by these methods and 68 will be discarded by these methods. So this was pretty useful because we could still use genomic selection to discard some lines, although there will be some lines that we will always miss because some of these might not be represented well in the training population. So some of the lines might have a really high yield, but the predicted values might be low, so we should always expect that. So we are still working on minimizing or trying to minimize those orange and blue regions to make sure that we have a good overlap between phenotypic selections and genomic selection. However, all this is assuming that the phenotype is a real true breeding value of the lines. But sometimes for the trait like grain yield, that might not be the case. And I'll explain that a little slide later. Next slide, please, Umesh. So we've also done this for stem rust. And at a selection intensity of 0.1 here, as you can see, a lot of lines, next, Umesh, a lot of lines are discarded by both these methods. About 80, that should be greater than 80% of the susceptible lines can be discarded for stem rust. And some of the top resistant lines were not selected, were not included. And that is something that we should always expect because there's always novel variation, and that's not represented well in the training population. So this gives us a good indication that for stem rust, genomic selection can be used as a very good discard tool to discard the susceptible lines. Next slide, Umesh. So we also looked at comparing genomic and pedigree-based predictions, and we did this for the 4 different nurseries. And the red bars here show genomic prediction accuracies, and the yellow bars here show the pedigree-based prediction accuracies. And there are 2 panels here. The one on the left shows lines that have no full SIBs and just 1 individual per cross. So if you just have 1 individual per cross, about 300 lines in every nursery, then you can see we do have a slight advantage of using genomic-based relationships compared to the pedigree-based relationships. But if we look at the right side panel, where you have at least 1 full SIB in the training population, then you can see there's not much difference between the genomic and pedigree-based predictions. And the lessons that we had from this analysis was that, including full SIBs, as we all know, the more genetic relatedness, and it almost doubles the accuracies compared to using lines that don't have any full SIBs. And one more interesting fact about our nurseries is that about 50% of the lines, so if we have 1,000 lines, about 500 lines in every nursery has no full SIBs. And the remaining lines that had at least 1 full SIB, they have a minimal variance for grain yield. So the standard deviation for grain yield is very less because all these sister lines were highly selected for superior grain yield. So the key lesson here is that when there is minimal Mendelian sampling variance, there is no scope for genomic selection to outperform pedigree-based predictions. And that's why at this stage and the highly selected elite line stage, GS might not be very effective in our breeding program. Next slide, please. And one of the things for dealing with grain yield here is that when we train a model using a variable like grain yield that can change across years, and as I showed before, we have a variation of 0.2, and then we use it to predict, again, another grain yield variable that is again variable, then it might not help very much for predictions. Next, please, Umesh. So either we have to increase the reliability of predictions by using well-replicated data rather than using single-year data, or when we make our correlations or prediction accuracies, they should not be estimated from using single-year performance, because then the accuracies will be biased because the phenotype is variable. So one of the things that we could do is probably minimize replications or substitute one of the replications that we use in the EYTs with GEBVs, because our heritability is almost similar to the accuracies that we have from our cross validations. Next slide, please. And we also tested the impact of marker density and missing data on these predictions. And all the results I've showed you before are using about 2,000 markers. So we also used less stringent approaches for filtering for missing data. And we had two other sets of using 9,000 markers and 16,000 markers. And very interestingly, all these markers had about similar accuracies. The increase in accuracies from using 2,000 to 6,000 markers there was some increase, but this was not very significant. So we realized that markers are not a big problem, because if you have an accuracy of 0.7, and if we divide it by the square root of the heritability, you're still getting an accuracy of about 0.9, and that's how much you could do with the markers. And moving on to the last slides. So how are we planning, Umesh, next slide, please. So how are we planning on using all these results in the breeding program? So we could use GS for selecting parents that we use in the crossing blocks. And then we are also, might be interested in testing parallel schemes, just combine GS and speed breeding, or do just GS and compare the gains with traditional breeding. And then GS should be tested for early generation selections here. And we have to evaluate cheaper marker platforms that Susanne is currently testing on, and use GS to test on subsets of families. For example, as we have 1,200 crosses, about 1,200 crosses with 300 individuals per families, we might not be able to do it for all the lines. So we might test it on subset of families. And next slide. And we have also used genomic selection to scale up selections to earlier generations. So you use 1,000 lines to predict 10,000 lines in the yield trials. So that has resulted in a cost savings of about $600,000 US, especially for quality, where we can't evaluate so many lines, about 10,000 lines for all the different quality traits. And then for stem routes, where genomic selection has really good accuracies, again, we just do one replication for 10,000 lines because of the cost of phenotyping. And this is a stage where we can potentially use genomic selection. And in the elite yield trials, although we do not have a very good advantage over the pedigree, we still can save by substituting at least one replication with GEBVs and use GS for multiple traits. We have about 20 to 30 different traits. So the cost per trait can be reduced, and we can use it across different traits. Thank you.
Okay, thank you, Philomin. It's my turn, Umesh Rosyara. I just want to go through the implementations, how we are doing across the programs, including some of points already made by our colleagues. So essentially, implementation requires effectiveness, efficiency, and relevance. We all talked about that, relevance, how good our predictions are, and how. Then another part is efficiency, how efficiently we can implement. Otherwise, if it's a burden to the breeders, then probably it's not adopted. So we still need to think about that. So we always think about the cost of genomic selection with cost of phenotyping, but that's another argument. If you have greater genomic rate of genetic gain is double, then it may be even invaluable. So then, which can be like expressed in terms of the monetary value. So that's also another important. So as Philomin said, we're thinking in different ways and different directions how we can fit in our breeding program. But another part is implementation requires efficiency. So there are other components to that, to implement it in a proper way, in effectively, efficiently. So, so as we discussed, we are constantly testing, implementing new models. We are testing and deploying different platforms, whatever we comes to. We're not bored yet of testing different platforms. So one of the issues is dealing with missing data and haplotypes. There's another things we are looking at. And one of things we may be thinking in future is combining genomic selection with the speed breeding, as a wheat program has a speed breeding greenhouse in Toluca, I think will be implemented if we can come out a model that genomic selection. So Susanne has some project to have some proof of concept of integrating genomic selection with the speed breeding. Yeah, that are the efforts so going on. They don't have a result set, some of them have, so it's ongoing effort. So the strategy on implementation can be a variable, like one would be maximize accuracy and finding genotypes that likely succeed. Another is discarding, probably you heard from Philomin and Poncho that discarding is more accurate than finding genotype that are likely to succeed. Maybe that's a good strategy for our future. So another thing we have not probably looked is the speed, reducing generations, which is kind of, we need a very extensive type of evaluations to do, because it needs like it will have a bigger impact on the breeding program itself. So we may be thinking on different ways to, so cost benefit analysis is not straightforward as we think, and evaluation of genomic selection models is not straightforward either. So implementation calendar, as you see, Susanne talked about the subtle breeding. So almost around we have two crops per year. So one in like this green is Obregon main testing site, and another is off-site like Albatan, where the CIMMYT headquarters is. So if we implement in 2 cycles, maybe it's too tight to implement. So far I think one season is, even with one season you need some time to fit, like genotyping, phenotyping, training of models, and the predictions, and so on. So it's very tight. So one thing we're looking at is the genotyping platform to increase efficiency and cost effectiveness, which is very important. Which has wide options, but most of like array-based are very expensive. But NGS provide the opportunity to reduce the cost. Again, the problem is the missing data and the number of useful markers. And now NGS-based marker, some of DART LD, which can cost down to $7 per sample, is being tested. And we are more hope on RAMS-seq, but which is not developed yet for wheat, which can reduce the cost down. So one of things we have been thinking about is development of practical haplotype graphs. We have a good discussion with Ed Buckler's lab at Cornell. So maybe that can help us to circumvent some of the problem associated with the marker platforms. So we're still looking for ideal platform actually. So we say less missing value is cheaper and it's multi-purpose. As see, one of thing is combining forward selection with genomic selection or marker back crossing. So where we have flexibility of picking our markers. Mostly NGS marker doesn't have that flexibility. That's flexibility to choose markers associated with the traits and then some more background markers so that it's a good combination. That same area within that cost, we can screen for markers as well as do some predictions or use those marker in prediction model like so that is our ideal thinking, but still we don't have a platform like that. So that's the ideal platform we are looking for. If you have any idea, just think about maybe our RAM-seq may have some potential, but we'll see how many markers we can have on that platform as we can pick markers.
Hi Umesh, this is Ramu here.
Ramu.
Yeah, so RH-AM-seq is definitely will be fitting into all these ideal platforms. Mm-hmm. So once you evaluate some markers, you can remove or add the more number of markers to the existing marker assay. And this is the PCR based, so you will get the less number of markers. It's approximately $5 per sample. And you can add whatever the loci of your interest. So you can fit into all your loci into the assay. So that can fit very well here.
Yeah, that's good. That's the ideal situation. Only our concern will be how many markers we'll get at the end. Or we need 2 arrays running. If the cost is even low, then we can run parallel 2 arrays, right? Like that will make number of marker enough, maybe.
Yeah, thank you very much, Umesh. We have about 7 minutes left.
Yeah, I'll just wrap up.
Yeah.
So improvement of models and implementation, these are different things we are still thinking about. As Susanne said, copy number variation is like across genome is one thing that never considered in wheat, I think. So implementation wise, one part is the computational infrastructure. In future, now we don't have phenotypic database is still coming up, and then Gobi is like being tested and developed, and we want to use that with connecting with genomic selection pipeline that we're developing with Gobi project. Within Gobi project, that will help. So I think that's all. We'd like to thank all the donors we have. Then I think we have few minutes left for questions.
Yeah. So anyone have questions for the CIMMYT with genomic selection team, please. Yeah.
Hi, this is Liz. Can you hear me?
Yeah.
Yes, please.
Hey, Umesh, and everyone in the CIMMYT Genomic Selection team. Thanks, that was a great talk. I had a question for Philomin about the number of markers used for genomic selection. Did you try testing smaller numbers of markers rather than just larger number of markers to look at the efficiency?
Yeah, we did. So we filtered markers based on the R-squared or LD, and we used even 200 markers. And sometimes what you see is all you need is about 200 to 250 markers to, at least for the EYT nurseries that I'm working with. So there's not a big difference between using 200 markers versus 16,000 markers. You might get increase that is between 0.01 to 0.1. And our average increase was 0.04 between these number of markers.
So would you consider using a smaller plex then to
Yes.
decrease the cost? Okay, great, thank you.
Thanks, Liz.
Hi, Philomin. I have a related question for these slides. So are these markers all random?
No, so they were filtered based on the missing data. So 2000 was for 90% presence of markers. 9,000 was when you have 50% present and 50% absent. And 16,000 was when you have 30% present and 70% missing. So they were all imputed. So it's both marker density as well as missing data, the number of markers.
All right. So would you consider imputations highly important in order to use low density marker technologies?
Yeah, I would say so. So if we have a few set of key lines that are genotyped using a high density panel, and then you have all the progenies or the parents genotyped using a high density panel, we could still impute it, the others that are genotyped on a low density panel. Yeah.
I have a comment.
Go ahead. Yeah, thanks, Pawan.
Do you have the slide that Philomin shows on the quality trait? On the quality trait, looking at the prediction accuracy using 9,000 and 60,000 markers. If you look at that prediction accuracy, if I am a donor, I will give $5 million right now. With this prediction accuracy, you cannot doubt about genomic selection. 0.7, 0.7, 0.6. I mean, this is something amazing. I mean, this is going to work. It's working already, right? And at the level of grain yield, a prediction accuracy of 0.4 that we hope to increase up to 0.5. I mean, genomic selection should work very well. If I were a donor for quality traits, I would say, I give you the money. Start right now.
My screen.
Yeah, sure. Go ahead.
Okay, so very quickly. So this is what is happening with our markers. So we have 78,000 markers initially, and the figure on the left shows how many markers we lose at a very low minor allele frequency and a high missing data percentage. So that's about 10,000 of markers where you lose at this stage. And the figure on the right shows about the 16,000 markers, which are well distributed throughout the genome. And in this slide, you can see 2,000 markers, which has about 10% of missing data. And as you can see, the markers are still concentrated on the telomeric ends, and you have huge LD blocks. But still, these markers are able to give you pretty much the same accuracies as using the 16,000 markers. So that's what is going on. We believe, as in wheat, the recombination is high on the telomeric ends. So you have most of your genes at those ends, and there are huge LD blocks, at least in our symmetry on plasm. So a few markers are still able to capture that variation among the lines. Thank you.
If just one word, one sentence to summarize.
Probably tested in the earlier generations, and where we will have a real advantage versus in these elite lines. So we will be looking forward for cheaper genotyping for at least a few families in earlier generations where we can test rapid cycling and real genomic selection.